Thank you so much. Today I would like to present some of my work about the interfacial segregation, and you will hear me speak about atom probe tomography and Auger electron spectroscopy primarily, but I will also throw in a little bit of TEM-based work. And for the structure of my talk, I would like to first talk a little bit about segregation. What is it? Why should we care? And then I will quickly review the background of the techniques I'm using. Then I will go through each of them one by one in a little more depth, talk about specific aspects relating to interfacial segregation, some pros and cons. And I will also share some of my own work. So in the end, I hope I can demonstrate how all those different techniques complement each other, and not a single technique reveals the whole picture, not even the mightiest of the techniques. You really need to look at it from different perspectives, and I hope I can provide you with some practical knowledge and some practical tools so you can ask yourself the questions that you need to succeed to finally do those interfacial analysis on your own. So first, what is...
Jonas?
Yes?
Sorry to interrupt. You're not sharing your slides.
On the screen. I'm sorry.
Nope, that was my fault. I took over and didn't remind you.
Perfect.
All right, looks good.
Wonderful. Great. Thank you for reminding me. Yeah, so about segregation. When in material science we speak about segregation, sometimes we mean different things. There are different phenomena called segregation happening on different length scales. For example, sometimes we talk about microsegregation. If you imagine a big slab of steel just cast, it's solidifying, and the composition in the center of the cast of the slab might be different from the edges. We also have microsegregation. When you think, for example, in dendrite growth, the composition might be different between the dendrite and the interdendritic space. But what I want to focus today is interfacial segregation in the sense of Gibbsian segregation, also sometimes called nanosegregation. And it is special in its kind that it is always associated with an interface that can be external or internal. That means the external surface of our material, or internal surface like interface like a grain boundary or an inclusion surface, something like that. And it happens always over very short distances of over only a few nanometers, sometimes even one atomic layer. And we see an enrichment over several order of magnitude, as you can see here. So how do we get those enrichment segregation structures? The mechanism I'm most working on is the one called equilibrium segregation. We have a system which is a very dilute solution. We have a solute that usually has a different, usually a lower interfacial energy, like a lower surface energy compared to the bulk, also a larger atomic radius. So the driving force for this kind of segregation is a reduction of the overall energy of the system by a reduction of the interfacial energy, as well as a strain relief from the lattice. There are other mechanisms which can produce a similar structure, maybe not as sharp as the equilibrium segregation, but similar. Different non-equilibrium segregation mechanisms can be caused by quenching or also by radiation damage. So why should we care about interfacial segregation? Well, one reason is that it can have quite severe consequences for our material properties, namely mechanical properties. We see a strong embrittlement of the structure, as well as our susceptibility to corrosion damage. Down here on the left, you see a very iconic image of the Hinkley Point A power station in Great Britain in 1969. There was a very big accident that is believed to be the first failure of such a turbine generator in Great Britain. And they could trace this burst back to a small crack, 1 millimeter large, caused by stress corrosion cracking. But the startling fact is that the material and the system was designed to withstand such a small crack. It should have been stable over the whole lifetime of the power power station. Now, what had happened is that the phosphorus that was in the steel segregated during the slow furnace cooling of this part, segregated to the grain boundaries, and brittled the grain boundaries, and made this whole thing susceptible to brittle failure. But there's also, like where there are challenges, there are opportunities. We can use like those segregation phenomena to change basically all, or like there's a potential to basically change all materials properties that are related to interface by so-called segregation engineering. So by doping, for example, certain elements and then designing a heat treatment that enriches them at the interfaces, we can, for example, change transport properties, grain boundary diffusivities, and so on. So a very interesting tool. And one case where this is applied is in the chemistry of catalysts. If you imagine you have a chemical reaction, you want to speed it up with, let's say, a platinum surface, then of course you can build the catalyst out of pure platinum, which would be very expensive. You could also apply a platinum coating, but that might not always work, right? If you imagine you have a very porous open structure with a high surface, like a high surface area, and that might not work. So the most, I would say, elegant way to get this is to have a matrix, which is like microalloyed with the element we want to have at the surface, for example, platinum, and then we design a specific heat treatment. So we get a nice atomic layer just on the surface, and like this is independent of any structure. So very efficient way to use, to be sustainable, to use our like the elements we have. What I'm working on is the potential of a tin addition to improve galvanized coatings, especially when we want to use newer grades of steel, third generation advanced high-strength steel in the automotive industry. We want to protect it from corrosion, want to coat it with zinc, but there's an issue, right? Like in such a hot dip galvanizing line, the strip undergoes a continuous annealing process prior to be dipped. And those alloying elements, for example, manganese or silicon, they are selectively oxidized in this environment. So they can form an oxide layer on the surface. That means when we dip the steel into the liquid zinc bath here, it might not stick, right? You see here like the bare spots. But the addition of only 0.05% tin proved very efficient to improve the surface quality. Here we can see bare spots, and like with the addition we see like no visual defects. So how does the tin does that? Well, tin is a surface active element. It has a larger atomic radius than the iron, a lower surface energy, and during the heat treatment, it segregates to the surface. So we have an enriched layer of tin at the surface, which has a trifold mechanism to improve our coating. It blocks the adsorption sites for H2O molecules, which is the source of our oxygen for the oxidation reaction. So less oxygen is supplied in the first place. It also decreases the grain boundary diffusivities. So we have a slower inward flux of oxygen, a slower outward flux of alloying elements like manganese. So we're slowing down the overall oxidation kinetics. Also, we see a change from a more like film type oxide morphology to more discrete nodule type morphology. That morphology is also related to better reactive wetting. So overall, tin can help us to be able to coat steel grades, which before are very challenging to coat at all. So if we now want to characterize such interfacial layers caused by segregation, we have different challenges. First, overall, we are talking about very dilute systems, right? Like 0.05 tin, that would be in the usual range of concentration. So even if we have a very strong enrichment over a few orders of magnitude, we are still talking about low absolute concentrations, right? So we need to have a technique that is very sensitive for low concentration. Also, in other situations where we measure enrichment, we have also the other side of the medal that we can check, have a sanity check, right? If I see an enrichment, I usually also see a depletion. But here in our case, because the bite concentration is so low, we cannot measure the depletion usually. Also, because we are talking about such thin layers, in the extreme case, only one atomic layer, we need to have a technique that is very surface sensitive, right? So ideally a sub-nanometer resolution, depth-wise. So far, all those challenges sound very similar to our usual challenges when we analyze thin films. But there's something special when we talk about real engineering materials, metals, for example. And that is that we cannot assume that our enrichment layer is homogeneous across the surface of our sample, right? We might want to analyze different grains, which are in the micrometer range, or we want to analyze the surface and try to find a spot where there's no oxide nodule, or we want to avoid a specific inclusion or surface defect. So we need a very good lateral resolution, but also we need to be able to get a visual feedback to choose our region of interest. That means all those techniques you will see always have the visual component, so like microscopy as its best. That also limits the techniques we can use. For surface layer or thin film analysis, we have something very powerful and quantitative, like secondary ion mass spectroscopy, but that is often not as helpful, right? We have to go more to the left side here in the diagram, I think, because we need the improved lateral resolution. Also, it would be nice to have access not only to the external interface, at the external surface, but also to internal interfaces. Then finally, something to think about more on the philosophical side is how do we quantify enrichment? Because concentration, usually atomic concentration, we could express as numbers of atoms per certain volume. But if you really have one atomic layer, how do you express concentration? So you could express it as a fraction of a monolayer coverage, an interfacial access, also pros and cons, and that is something to consider. So today I'm talking about how four different techniques play together to characterize our interfacial segregation. That is, as I mentioned, TEM-based techniques, namely EDS yields, in combination with Auger electron spectroscopy and atom probe tomography. So I would start with reviewing just quickly the solid electron interaction, because of the four techniques I just mentioned, three are based on the analysis of electrons. Right. So how does an incident electron, primary electron beam, interact with matter? Well, we have this very simplified three-step process. We have a high energy incident electron interacting with our sample atom. It is inelastically scattered. We create a hole in our material atom, and at the same time, the incident electron loses energy. That energy loss is quantified in yields, one of our techniques. But then we have the hole, which is filled by a relaxation process by a higher energy electron filling up that spot. And for the sake of the conservation of energy, they are either one of those two competitive processes. So either we have the emission of an Auger electron with a specific kinetic energy, which is measured in Auger electron spectroscopy, or we have the emission of a photon, right? So X-ray with the specific energy, which is measured in EDS. So those those two roads, I would say, are competitive. So Auger is more dominant for lighter elements. EDS is more dominant for heavier elements. Also more dominant and higher primary beam accelerations. Now, the practical side of our three techniques, we have TEM first. We usually we have to produce an electron transparent sample, so very thin. And there are different techniques. If you want to target a specific interface, flip lift out is usually the way to go. So we produce such a thin lamella. It is mounted on copper grid. Once that is done, it is inserted into our TEM here, and we turn on the beam, and we can record the EDS signal from detectors, usually inside the column, either before or behind the sample, or both sometimes, while the primary beam is conducted towards more the bottom of the instrument, where we have an electromagnetic prism that projects the beam on a screen, and that is the way how we get our yield spectrum. Auger electron spectroscopy happens in an instrument that is very similar to an SEM. Everything happens in ultra-high vacuum. You can see here our primary electron source, and here offset at an angle we have our electron analyzer. Both you can see also here in the photo of the analysis chamber. So the sample really doesn't need any sample prep. It can just put in the holder. It must be able to withstand ultra vacuum without outgassing. That's basically one of the few limitations. But that's it. No sample prep. Right? And here in the schematic, you can also see a second gun. It is a broad beam argon gun, which can be used for charge compensation, but more importantly for us, for elemental depth profiling by sputtering. Now, atom probe tomography, on the other hand, is a little different. No electrons are employed in this technique. Our sample is our lens, as we say. We are like the basic idea behind this is to evaporate a very sharp needle in high electric field. And first, we need to make the needle. Right? There are different roads how to do this. More commonly, the FIB road for interface analysis. And once we have this needle, is field evaporated in a controlled manner. That means synced with either voltage pulses or laser pulses. And the time the ion takes from the pulse until it hits the position sensitive detector here is used to calculate, the time of flight is used to calculate the mass to charge ratio. And then from the whole mass to charge spectrum, we can then infer back to the elemental composition of that specific ion. So just a broad overview. So you know, when I compare the techniques, you will have a rough idea on each of them. They're a very great series of CCM webinars, yields, or other TM-based techniques, very great and insightful. I can just highly recommend. They help me a lot. So let me talk about TEM-based techniques in depth first. What are a few pros and cons when it comes to interface analysis? Well, first, within one sample, we have access to both external and internal interfaces because we're looking at it in cross-section usually. We have that advantage. For example, in Auger, we usually only look at the outer surface. Getting access to internal interfaces is a little more challenging. Then we have overall a much larger sample volume from which we can choose in the instrument itself. It is much easier to connect the region we are looking into the overall surrounding microstructure. I will give you an example of that just in a bit. It is also the spatially most direct way of measuring, right? In Atom Probe, we are reconstructing a data set that is based on its evaporation or field evaporation characteristics. In Auger, we have to calculate, or we extract our spatial information from the interaction of an ion beam with the matter. So all those are secondary kind of ways how to get the spatial information. While in TEM, we just have our beam that scans over the sample. And here, if our instrument allows for atomic resolution, then it is more on the sample side to limit how sharp we see the interface in TEM. It is also non-destructive. That means you can make a sample once, you can come back, look at it several times. Once you have the sample, the acquisition is relatively fast. And one last big advantage is that inside the TEM, you also have access to different diffraction techniques like selected area diffraction that helps you to further characterize the interface, for example, in terms of misorientation, grain orientation, to further characterize the interface. Now, talking about the cons, well, of course, general point speaking against, or like making it a little more difficult, is that you have to have access to a FIB. It takes a little time and practice to do that. And also that the sample prep as well as the instrumentation can introduce different elements that will appear in your analysis, right? That can be carbon from a carbon coating, but sometimes also additional elements which appear in the instrument itself can appear in your spectrum. For example, iron from the instrument structure itself, or copper from your grid. If you're interested in especially those elements, you need to take care how to exclude that from your quantification. Then in general, I would say those techniques are less quantitative for analyzing enrichmented interfaces, because in the end, it depends like how sharp you see your peak in the elemental profile you do across the interface will ultimately depend on the curvature of the interface within your sample. Of course, going thinner will help, but in the end, in a real world sample, in a grown like in a polycrystalline sample, you will always have some kind of curvature. So comparing sample to sample and relating that back to, for example, different annealing conditions can be tricky. Now comparing our different analytical techniques, EELS and EDS. EELS usually has a better spatial resolution, also better energy resolution. It is more used for light elements, while EDS is better for heavier elements. Also, EELS reveals much more additional information besides a peak appearing at just a specific energy. We also have a very specific peak shape that can tell us, that will help us in identification, but can also tell us much more about like electronic structure. So I tried to do some EELS on my sample. Tin is a heavier element, so there was no success guaranteed. And in the end, I ran into a common problem in EELS, and that is that everything happens on a very strong decaying background. And also other peaks can have a rather large background. For example, one example of a tin-enriched surface that I had on one of my sample, I had found the enrichment in iron probe and Auger, so I'm quite certain that there was tin. But we can see here our tin peak lies right in the tail of our carbon coating. Also, if you compare it to a simulated spectrum, I use the Gatan EELS Advisor. Also very, I can just recommend it to give it a try before you go down and like make actually your sample. Just go to the EELS Advisor, enter your sample, and see how the peaks distribute. And we can see here, first, tin doesn't have a very dominant peak. It is more like a hump, I would say, and it's most prominent between 500 and 600 electron volts. And this is exactly where my sample, I do see an oxygen peak from oxygen contamination. So EELS proved to do not be very helpful in my case, but I got lucky with EDS. You can see here a very nice, clean EDS peak. I was lucky to not have any overlaps, making my analysis more difficult. And I was able to find tin at my external surface, and as well as at the grain boundary of my iron tin binary alloy. I mentioned before that the analysis volume we can pick our size from is much larger. So I tried to compare APT to TEM. That is roughly to scale, right? So the width of the sample we can analyze in TEM, we can get something 5-6 microns here. And if you look here at our reconstructed atom probe volume, this is really wider than 100, maybe 150 nanometers. So while atom probe, I would look very quantitatively at one specific oxide. Here I can potentially repeat in TEM. I can potentially repeat this kind of analysis for 100 different oxides if I wanted to. So that's exactly what I did. I probed different oxides within my sample. I looked at the interface of the iron with an external oxide nodule. I tried different internal oxides, here larger one, like more than 100 nanometers in diameter. But I could even find tin at like very small ones, which were like barely 10 nanometers wide. So it really helped me to confirm the presence of tin at all the interfaces I was interested in. So much about TEM. In the end, what I would say for me were the most important factors contributing to the overall interfacial analysis were that I would have access to internal and external interfaces. I can probe many different sites within one sample. Also, I had the most direct spatial resolution of the interface. So now, in my next section, I will talk a little bit more about Auger electron spectroscopy. First, you always hear Auger electron spectroscopy is a very surface-sensitive technique, but the question is why? And you might have heard that people say, yeah, Auger electrons have such a low energy, they're not able to escape from deeper than a few nanometers. And that is not technically correct. Auger electrons we deal with have electron energies between that are like often around 100, between 1,000, so a couple of 100 electron volts, while the cutoff in the definition for secondary electrons is like 50 eV usually. Nonetheless, if you look at those like diagrams, Auger, of course, is always like very surface sensitive, while secondary electron, our signal comes from a deeper depth. So why is it? The big difference between secondary and Auger electron is that Auger electron spectroscopy is a spectroscopic technique. So we care about the specific energy of the Auger electron that we detect. Only Auger electron that have their original energy, original kinetic energy specific for this Auger transition will contribute to the peak. The rest will go into the background. While if you think about secondary electron image, basically any electron that makes it into the Everhard-Thornley detector, for example, will contribute to the signal, will contribute to the contrast in your image. But in Auger, only electrons that were not inelastically scattered on the way out contribute to the signal. That means the one material parameter that makes Auger surface sensitive is its small mean inelastic mean-free path. So how surface sensitive is Auger? It is sometimes not so easy to say. That is because it is generated at different depth within our sample. Here we can see the escape ratio from the solid surface versus the escape depth. And we can see that the signal follows a decaying exponential function. And that would mean, for example, that 86% of the signal are generated within the distance that is twice as long as the mean-free path of the Auger electron, right? So you could say, yes, the signal or like the information depth is twice, or if you base it on the 95% signal, you can say it's like 3 times the mean-free path, but you have to consider that most of it is generated very close to the surface. So when we talk about the mean-free path, like one distance or twice the mean-free path, how much is it actually? And we can see here from the diagram, for the Auger electrons, we usually look at here between 100 and 1,000 eV. The mean-free path is roughly about 1 nanometer, right? So we can say for most of our systems, 86% of the signal is generated within the first 2 nanometers of the system. But to be more precise, we have to look at our very specific material system, our specific Auger transition we're interested in. So how does Auger electron experiment work? Here we can see the raw data that we would collect from our experimental setup, a differential spectrum from one of my tin-enriched samples. If we want to do elemental depth profiling, we would just like repeat this acquisition of this of those spectra, but like between each spectrum, we would turn on the ion gun for a specified amount of time. And so we would end up with such a set of different spectra. What we actually want is a depth profile. That means concentration versus depth. So how we get to that? Well, we have to apply different quantification techniques, and we have to apply them in like the 2 dimensions, concentration and depth. And I will talk first about how to extract the precise concentration from an OJ spectrum. So not to scare you here with all the equations, just for some demonstration purposes only here. For a homogeneous material, A and B, we can approximate just a very first order approximation. I can say, how do we get our atomic concentration or the atomic fraction of our element of interest? Well, we measure the intensity. Intensity, we usually it can be defined as the area under the curve of the absolute spectrum, but usually it would be measured as the peak-to-peak height in the differential spectrum. It is just the intensity of the element we're interested in versus the sum of the intensity of the rest of the elements, and each of those intensities is normalized by the intensity of the pure element. If you have a standard, you can measure it yourself. You can also look at relative sensitivity factors, which is basically the intensity of the pure element normalized by the intensity of a pure reference element, usually silver. But that is not enough, right? If we have a mixture, and we know in like many cases, a mixture is more than the sum of its elements, we need to take that matrix into account, like that mixture. So we introduce in the quantification a so-called matrix correction factor. And what this matrix correction factor does, that is corrects for like the difference between pure element and mixture in 3 different ways. First is a backscatter correction. That takes into account that the OJ electrons are not only generated by a primary beam penetrating the sample, but also by the backscatter electrons on the way out. We have a different attenuation length, so like related to this inelastic mean-free path, and also we have a different atomic density. Now, if we look at thin films, things get even more complicated. Here, like this is just a very rough approximations. There are other equations probably filling the whole page. Just a few things you will notice, that here the relation between the surface concentration of our element B and the intensities we get, they scale with the angle between the analyzer axis and our sample normal. That will get important in just a bit, but it is also dependent on the overlayer thickness. So like that is not longer a unique relationship. So you might ask yourself, how do you get all those numbers here, right? Like where do you get them? Well, you could look up, like you could go through different handbooks. There are different empirical equations that you can also consult. What I found very helpful, interesting, is a program called SESA. It is published by NIST. Simulation of electron spectra for surface analysis, and it works in 2 ways. You can use it as an expert system to retrieve all those parameters from databases. But what I also found really helpful, it has a Monte Carlo simulation tool inside. So you can set up your sample, you can define different layers, you can even include roughness, go to different overlayer geometries. You can define the peaks you want to look at. You can set up your source and the geometries just as if you would do in an actual OJ instrument, and you can simulate the OJ spectrum you would get. So for example, if you're uncertain which equations from before you can use, you can always compare that to a simulated plot, or even you could kind of reverse engineering your spectrum that you get from the experiment and just try different geometries until they match. So I found this tool very helpful. But SESA can also help us with the different challenge we encounter when analyzing thin films. The problem is, once the thickness of the overlay is thin, like thinner than the information depth of our signal, there are different things to take into account, right? Like we have, for example, the shielding of the matrix signal by the overlayer, but also that the backscattering characteristics are now more more heavily influenced by the matrix versus the overlayer. And as I explained before, the connection between the composition and the intensity is not unique anymore. So that means the different combinations of concentration and thickness will produce the same spectrum, right? So I simulated that spectrum, but those two geometries result in the exact same spectrum at one fixed angle. So, but I would like to know which one do I actually have in my sample? Well, the techniques that can help us is angle-resolved Auger electron spectroscopy. You see here that it scales with the angle theta. I will just show you which angle that exactly is. So by changing that angle, you will see that based on the thickness of the overlayer, the relative intensities will change dramatically. How would I go about this? Again, you can simulate it in SESA. You can there's a geometry tab where you can insert 3 different orientations, 3 different angles. Here you have your static reference system, and then you can see first the axis of your surface, like your sample surface normal, that would be that one here, as well as the analyzer axis here and the source axis here. Just keep in mind that while here in the setup you can change all 3 of them, that usually the analyzer axis and the source axis are fixed. They're defined by your instrument. Just the surface sample normal, like that angle, is something you can actually change during like an acquisition. And like that is a simulated spectrum, or like different simulated spectra for different emissions angle. One for the scenario where I have a homogeneous enrichment layer, and we can see regardless of the emission angle, the relative intensities stay about the same, while when I look at the atomic layer configuration, like the right example from the slide before, we see that as we go shallow, we have a shallow emission angle. We see that the element that is present at the surface gets more and more prominent versus like the matrix element. Comparing this kind of simulation to an actual angle-resolved experiment I performed in geology on my sample, that we can see here in black, my experimental data follows much more closely to the homogeneous type of scenario. So for me, I could conclude that my angle-resolved AES supports more the model of a wider enrichment layer, not as sharp as just one atomic layer. So far, I talked about the quantification in the dimension of concentration, but we also care about the depth. How do we usually go about that? Well, the instrument parameter we control is the sputtering time, and we use a fixed sputter rate to convert that into a sputter depth. And those sputter rates are calibrated usually using let's say a 100 nanometer or a thinner silicon oxide thin film on a silicon wafer. But it is not so easy to make that conversion back to your actual depth that you're probing. The sputter rate is only specific for the geometry it was recorded for. So the angles, the tilt angle, for example, has to be specified. It cannot change like later. Otherwise, you just have to perform the calibration again. It is also highly material dependent, right? Even if you look here on like that example for different sputter rates, you can see, for example, iron system I'm interested in, like the sputter rate can span from almost 20 to 40 nanometers per minute for that specific setup they tested. And such a wide spread, of course, can come from different alloying additions, But here, for the case of pure iron, it is just different crystal orientations, right? We have to take that into account. Different crystal orientations will have different sputter rates. They will be more or less susceptible to the impinging argon ions. You also see shadowing effects from surface feature. I will give you an example in just a bit. We also have to consider that the argon ions that impinge on the surface will have an interaction with our material. They can induce roughness, they can cause mixing of the outer layer, they can cause argon implantation, as well as amorphization, or even a change in the charge state. Right? So if you see a shift from more peaks that are more characteristic for a metallic sample, but then you see it shifts more to the oxide, it can also be that this is just caused by the argon. So to take home from that is our conventional approach gives just a rough estimate. There are very sophisticated quantification techniques that exist that first characterize the influence of the beam on all of those items separately, and then take it into account in like one model, and then try to deconvolute like the different contributions to finally get like the real true composition. So for example, if you're interested in that, you can look up the MRI model. It's very helpful, but it's also very sophisticated because you need to consult all those different techniques from Auger in order to set up your model. Also to be noted that the access to internal interfaces is limited. So far, we are only talking about probing the external surface. That works quite well in a limited range of depth. Like tens of nanometers is usually no problem, maybe even like hundreds of nanometers, but like that's it. What usually doesn't work very well is when you want to look at the segregation below a surface feature. So you have to sputter through that feature. That usually doesn't work very well. I tried it out. I wanted to look at the segregation here. You see in cross-section the segregation at this oxide-metal interface. But you can see even after prolonged argon sputtering, because of the geometry, because of the different materials, different sputter rates, and like the non-flat surface, we see a strong shadowing here. And I was not able to resolve any tint signal in that way. The alternatives you could consider, for example, you can get rid of that surface layer by other means. For example, a dissolution technique. Here, hydrogen peroxide worked quite well, but of course, you need to be sure that this treatment doesn't further affect the concentration of the element at the surface. So I just said that accessing internal interfaces is a challenge. There is one way to do it that usually works well for grain boundaries or like larger interfaces, and that is cryofracture. So cryofracture is quite interesting. You machine such matchstick samples, like they are notched. Here you can see they are put in such a holder for the Auger. They're inserted into the instrument. You can see here is our like buffer chamber. They go into analysis chamber. We move them back into a specific cryo chamber, and the cryo chamber is then filled with liquid nitrogen on the top. You wait for it to cool down, and then you fracture it. That is probably the only time you're supposed to hit a microscope with a hammer, but you actually have to give it a good smack to actually cause that fracture. You move the fractured sample back into the chamber, and you look for the intergranular fracture facets. It is sometimes not as easy as it sounds, because first you need, in order to characterize segregation at the grain boundary, first you need to cause intergranular fracture. That works well with species which cause a further embrittlement. But if the species is either like very, like the segregation doesn't happen to a strong degree, or it is a species that even strengthen the grain boundary, then this is very challenging. Also, you can only analyze 1/2 of the interface, right? The other piece will be lost inside the instrument. So how the segregated layer distributes between the 2/2 of the interface. Sometimes it's a little controversial. Some people talk about like the cake layer model, where it is just on one side and not on the other. Most people say it is equally distributed between the two interfaces, but experiments show that it is not as easy, right? It is about 50-50, but there's a non-negligible amount of scatter in that. Also, if you want to use this data to calculate any thermodynamic properties, you must be aware that you're preferentially fracturing along embrittled grain boundaries, right? So your results might be biased towards more the highly decorated grain boundaries, because for example, like low angle grain boundaries or like grain boundaries which you have less segregation, they will not lie in the fracture path, right? Like you will not consider them in your analysis. As you can imagine, all those fracture facets have different angles, different orientations towards analyzer, towards a primary beam. That can also make it difficult to sometimes access and get like good signal out of one specific fracture facet. So another thing to keep in mind that the time you have to analyze such a fracture surface is very limited. Even though it's an ultra high vacuum, you see some contamination over the time, you see some carbon depositing on the layer. So usually, let's say you should get this done within an hour before the carbon concentration becomes too dominant. Auger also provides a very powerful mapping feature, right? Here we can see elemental maps of, for example, tin at the surface in relation to the manganese oxide nodules and also the iron. I think we just take a second here and really give the kudos to Auger in that, because we are mapping something that is only a few nanometers, potentially even thinner at the surface, with the lateral resolution of tens of nanometers, with zero sample prep, no FIP is necessary. So I think it just demonstrates how useful Auger can be, right? Like that would usually be like a mapping of such fine surface features usually would require TEM and time-consuming sample prep, and here we can just put it into the Auger and look at it right away. Some strategies to keep in mind to improve our resolution for the maps is using a higher voltage and a lower current. That would give us a finer probe. Unfortunately, higher voltage also means lower Auger yield. Of course, lower current also means lower signal. So to compensate for it, we need to increase our acquisition time. We need to have a frequent drift correction. You can see like those lines here, like that was drift corrected after every second line. Maybe after every line would have been even better. And also setting up the secondary image to low magnification and then acquiring the Auger map in a reduced area helps with the drift correction. Just so far about Auger. In the end, what contributes most to the analysis of interfacial segregation, like that was this, very helpful in Auger, is that I have unambiguous elemental identification. I have not only the peak position as I would have in EDS or Atom Probe, I also have a very specific peak shape, which further helps to identify it. It is, of course, faster. It requires less sample prep than the other techniques. That allows me to get better statistics on my samples. Also, with the angle resolved Auger, I have the ability to make this monolayer or like this atomic, like this very thin film distinction. Let's say a few angstrom versus a few nanometer, which would be difficult in the other techniques. For example, where Auger was very helpful for me, that here I wanted to analyze the tin enrichment at the surface of many different samples. So those are 4 different alloying systems. I wanted to probe 20 different annealing conditions, so I had over 150 samples, and like that would just be not be feasible with TEM or Atom Probe. And quite interesting, I found out that for systems, I have an enrichment of between 30 to 100 times the bulk concentration, and I don't see a definite trend with thermal temperature. And also, interestingly, no effect of the bulk manganese content. Now talking about atom probe tomography. This section is structured along our sample or atom probe tomography workflow. Starts with sample prep, acquisition in the instrument itself, the data reconstruction, and then finally the analysis of our reconstructed data set. I will spend most time talking about the sample prep. That is like very, as I said before, the sample is our lens. So this is really crucial, especially when we talk about interfaces. Usually in atom probe, we have the choice between two different sample prep roads. That is electropolishing versus FIP. For interface analysis, we would usually choose the focused ion beam road just because we can target a specific interface much more easily. And also in the FIP instrument itself, we might have access to different analytical tools like EBSD, for example, that can further help us to find our interface. Electropolishing for like a very narrow range of conditions, it might still help. For example, if you have a nano-grain material and you know, like you will have enough grain boundaries within any type of sample that is, let's say, 100 nanometers long, then okay, go ahead and use electropolishing. But focused ion beam is usually the technique to go. Then, of course, we need to find our interface. That can sometimes be quite difficult, especially when we talk about grain boundaries. The grain contrast might not be, like the orientation contrast might not be so great. So you can employ different diffraction-based techniques to help you first find a boundary, or maybe even like something like a prior austenite grain boundary that can be done inside. If your FIP has this capability, it can be done inside the FIP. For example, using EBSD, you can find your boundary, but you can also further characterize the grain boundary in terms of different misorientation or precise crystal orientation, and then you can selectively target a boundary with your desired properties. Because those techniques are usually too slow to be done live. You will usually like during the milling, at some point it is so small, the contrast is not very great, so you might lose track of your grain boundary, and you just want to confirm if it is still there after your prep. You can also do that and just check. You can do that again, EBSD, or you can also come up with your own correlative workflow together with TEM and use, for example, selective area diffraction. Also very interesting techniques. Now I want to talk about capping material, and this is really something that for me proved to be crucial. When we talk about capping material, it's different from the material we usually deposit in the FIP to just protect the surface. There we usually use tungsten, something really hard, something that is not easily buildable with gallium, something that will stop the gallium or any other ion you might use in your FIP to penetrate into a sample. But exactly those properties will make it difficult to run in the atom probe, right? Like it requires a very high electric field to be evaporated. If you have some tungsten left near a sample, usually you will experience fracture. So capping material is different. A capping material is designed to be run as part of your sample. If you, for example, are interested in your sample surface and you imagine you're milling a needle out of your sample surface, then the very outer part, the part you're interested in, actually at one point will be milled away, right? So having a layer here, like the dark one here, for example, is chromium, will help you to be able to move that interface of interest more from the apex towards like, let's say 150 nanometers from your tip apex, just to be able to observe the interface as with a larger field of view. Also, it helps to preserve the original interface. So how do you choose the material you use for the capping? Well, first, of course, you're limited by what's available to you. What techniques do you have to apply the coating? So you need a coating that's about 300 to 500 nanometers thick. It should be smooth. It should be non-porous. The process itself should not be damaging to the sample, and you should avoid any contamination. So that will definitely limit you in your choice of materials. Then the next step, absolutely crucial, you need a good adhesion between the cap material and the base material. If the adhesion is not good, you will load your sample into the leap, and you will get fracture at one point, and you won't be able to extract any data that you're interested in from your interface at all. When choosing the material, you should also consider the grain size that the capping material will have in the end. We either want something that is amorphous or with a much smaller grain size than your material, or than the tip, or a much larger grain size. The worst case scenario is that our capping material will have a grain boundary just on top of the cap, because as I said, different grain orientations can have different milling rates. This will be detrimental towards to the shape of your sample. Also, it should have similar evaporation characteristics like your base material, just to avoid fracture, to reduce facial aberrations. Also, maybe a secondary thing to consider is that nice contrast, nice elemental contrast is good for sample prep, because you will be able to more easily track your interface during fabrication in the FIB. Also, you should consider that for some specific material combinations, there are secondary effects. For example, using aluminum as a capping material might be good in all those other aspects, but if using a gallium FIB, it might still not work, because gallium is very drawn to aluminum grain boundaries. It will penetrate the aluminum grain boundaries. It will be present, change the chemistry, also embrittling them, so it might lead to premature fracture. And then also, a very important last thing, you should already have a rough idea what your mass spectrum in the end looks like, just to make sure that your capping material will not have any significant overlap with the species of interest you want to look at. So how would you go practically about finding a capping material? You could look, for example, at this periodic table provided by Chemica, which is the atom probe company. That works quite well for pure materials. Just be warned that alloying can, of course, change all those values quite severely. I'm interested, for example, in iron. So in my own journey in the atom probe world, I started with a chromium cap, because that is what has worked very well in the past. And it ran very well. But because of the way it was sputter deposited, and we know chromium is easily oxidized, I ended up having a lot of residual oxygen in my cap, which usually is not such a big problem. It still ran well, but because I had the oxygen, I acquired it in laser pulse mode, which also promotes the generation of those molecular ions. There are two molecular ions, Cr2O in a 2+ charge state, as well as FeCrO in the 2+ charge state, which were lying directly inside my mass spectrum range that is covered by tin. So by having those molecular ions, the amount of ion counts I could use to quantify my tin were reduced by 70%. So basically, I had, of course, the overlap with iron. I could not resolve. It's just a part of my system. So in the end, I could base my analysis only on 2 peaks with only a fraction of the counts. So that was not optimal, as you can imagine. So I went back to the periodic table. Right here, you can see the 33 would be the field. I think it's volt per nanometer, the field in which the most common charged state ion would evaporate. So we can see basically all those materials are pretty close. right? So, okay, like what can you try else? Well, cobalt is known to not have great adhesion, so that's out. Nickel sometimes can have problems with like the grain size, as I said, can be detrimental to the shape of your tip. So I said, okay, let's go and try copper. And copper really worked well in terms of the mass spectrum overlaps. I could resolve my tin much better. Now, a different challenge I ran into that again, the copper was contaminated with oxygen, and now the evaporation rate, or like the field at which it evaporated, was much lower than the one of iron. I mean, I was lucky that it didn't fracture. Like here, like going from such a low field to a high field increases the danger of fracture. It also increases spatial aberrations. Some other aspects to keep in mind when doing the sample prep. Here, the overall sample orientation. If you have a multi-layered structure, you can consider either running it what I would call the conventional way, right? You would, if you see that sample like that in the FIP, you would just mill out your tip as it is in like the like top-down kind of approach. But you can also consider running it upside down. If you want to run upside down, it's not as easy as just taking a tip and like turning it around. You have to actually fabricate the tip with an extra rotation step in the FIP. So that makes it also a little bit difficult. But here is an example where by changing the running direction, there was a boron doped layer that could be well resolved in what I would call the upside down direction. But it's also like almost no visible in our conventional running direction. So especially if you have a multi-layer structure where there's oxygen involved, turning the sample around might be worth a try. Sometimes it doesn't work as well. For example, I also tried it with my sample, but because I had the oxygen contamination, having this oxygen contaminated layer between the post and the sample proved actually to be detrimental to heat transfer. And if I'm in laser pulse mode, it is the heat transfer characteristics that also influence my mass resolving power. So I, for example, continue to use a conventional way. But additional to the overall sample orientation, we also should consider the interface orientation within one sample. Usually you want your sample, like the grain boundary or the external interface, to be perpendicular to the axis of your sample. That will help to give it a better tip shape, because you won't have a different or like you try to avoid, in the worst case scenario, to run into the case where you have different milling rates, but it also helps with the local magnification effects, like during the run. But just keep in mind, having a very perpendicular interface usually means a reduced contact area. So it really is it comes to the Kevin material needing to have a good adhesion to your sample overall to avoid fracture. The other important things to consider here, just really quickly, in the acquisition, because they are so prone to fracture at the interface, you really have to balance or like change the parameters to balance yield. That means the sample survives the acquisition versus data quality. You might consider changing to laser pulse mode if you're not anyway doing it that way. Lower your detection rate, increase the laser pulse energy, or ultimately you can think about increasing your temperature, all that to be a little more gentle on your sample. In terms of reconstruction, now we know, because we are running through different materials, the voltage curve will not only change because based on the tip radius, but also based on the chemistry of the sample. So we cannot use that as our sole base of our tip profile reconstruction. We usually use an SEM micrograph as we prepared in the FIB, we take an image at the end of the tilted specimen. Like that would be like the starting point for our tip profile reconstruction. If you really care about spatial information, you could go beyond that. You could take another FIB, another SEM micrograph post-acquisition just to see how much material you evaporated. If that is not enough, you can also consider taking a TEM image before, like at a flat orientation, to avoid any skewing from the tilt. When it comes to data analysis, there are two main things to consider. First, spatial information, that is the width of your interface that you report. Just be aware that here other artifacts like the evaporation characteristics, local magnification effects, and so on cause widening of the interface. Right, just to keep that in mind, even if you know in a different technique, you say an atomically sharp interface, but it spreads out over 2 or 3 nanometers in the aperty, that is something common to see. Also, expressing compositional information, I will show on the last slide. Sometimes it's not that easy. You can express it as an absolute concentration, like your enrichment, or you can express it as an interfacial excess. For example, case here from my samples, I have a region of interest. I lie across the interface. I look at the concentration profile, and if I really want to reduce it to one data point, I could, for example, report the maximum concentration. The alternative would be using the Gibson interfacial axis. That means projecting the whole enrichment into one plane, right? Like reducing the spatial kind of coordinates by one dimension. If you have a perfect sample that has a constant density that would somehow be related to the area under the curve, if you can see here, just for illustration purposes. But the way how we calculate it, it helps us to make our number like more robust, like less dependent on, for example, the choice of bin width, and also it can compensate for change in density, right? Like we would usually plot the cumulative number of the counts of the species we're interested in versus the cumulative counts of all ions. We would use calculate the step height here. That would be our, like the numbers of atoms that are associated with the interface. And we would divide that by the area of the interface, like the area where we took this data from, and correct that for the detection efficiency of our instrument. But it's always like there's no perfect solution to it. Always like reducing such a complex data set to one number is difficult. And you also should take into account that for both ways of looking at it is important that the region of interest, like the data or the region where you're extracting the data, should be perpendicular to the interface, so that the interface appears as sharp as possible in your data set. So finally, what does AtomProbe contribute? It is inherently quantitative. It gives me access to internal and external interfaces. And it also has tools to deal with interface curvature within our sample, right? Like the one thing that TM couldn't do for us. So this is the overview of the 3 techniques. I hope it was helpful to you, to your own journey in the world of interface analysis. Of course, I have many people to thank. My supervisor, Dr. John McDermott, for supporting my work, all the members of CAMC, all our partners and collaborators who made this work possible, but of course also to the CCM and all its great staff with the patience and expertise. Without you, that kind of work wouldn't be possible at all. So thank you for listening, and looking forward to any questions.
If you have any questions, please place them in the Q&A or the chat, and I will ask them now. I do have a question. This was a great presentation, and you've done so much work. For any new students out there that are in the area, obviously they can watch your presentation, but do you have any recommendations for them based on sort of how you started to the point where you're at now?
Yeah, I think it makes sense to use techniques which require less input first and then go to the more specific techniques. So for example, if you consider doing atom probe or you already have the idea that you could need atom probe down the line, that is usually not the first step because you need a lot of input information for atom probe, right? For example, a mass spectrum can be very tricky to resolve to identify all the elements. So you usually already need to have a pretty good idea what the composition looks like. Something like OJ, I feel, is a good starting point because, as I said, elemental identification is usually pretty good. And you also have the direct like visual feedback where you do your analysis and what your sample looks like.
Great. That's a a really good point to like start with, I guess, the simplest technique that can give you really rich information and then kind of take it from there as you need more detailed work. Thank you. I'm not seeing any questions coming in. I'll give it a little bit more time. But it was really a great presentation just to show how really you can use these instruments to fully interrogate your sample in very different ways. And pull out such useful information that with only one instrument you wouldn't be able to do. Okay, well, with that, I think we will wrap up. If you have any questions, please feel free to reach out with Jonas. I see his emails there, wagnej5@mcmaster.ca. And also feel free to reach out to the CCM or CAMC, and I'm sure we can get you in contact with them or help answer any questions as well. So thank you, Jonas. This was a great presentation. I really appreciate your time and effort.